Good afternoon, everybody. Thank you for coming for the final seminar of the term. We have had an excellent selection of the speakers, and we're going to finish in a high note. Today, we have the winner of the doctoral dissertation seminar is Dr. Zheng, who was in the group of Professor Luca Daniel. And he received the award after a careful consideration of everybody that applied to the award. We are unanimously giving the award to him because we found it very exciting, his results and his approach is a work of great importance to both people that do circuits and people that do MEMS. And anybody who has gone into a clean room knows that the killer is the variation in the fabrication, and because of that you need to come up with all these strategies, tuning and all that. So the good news is that there's help, and that's what the PhD of Zheng is about, which basically cuts in 100 times the time it takes to simulate the structure so that you can put the feedback in the loop and get closer to the goals than before. So the award comes with a certificate that is going to be given by Professor Jesus Del Álamo, the director of our lab, but a proper award that you're going to probably show in your living room is on its way. So I'll hand over the microphone to Jesus, and let's...
Thank you, Luis, and thank you for managing the MTL seminar series this term and ahead next term. This is a great service to the MTL community. We had a very strong program this term, and I'm looking forward to more exciting seminars in the next term. And thank you also for participating in the selection of our doctoral dissertation winner this fall. I'm delighted to give the award to Zheng, who is now with Argonne National Labs, and I also congratulate Luca Daniel for his mentorship of this research. So I'll give you your award. We have, okay, come over here. Yeah, you can have it. Okay. All right. Thank you. Well, we can then move on to your talk. Thank you.
Yeah. So Zheng, the stage is yours. You can start whenever you want.
Okay, thanks everyone for attending this seminar. Today I will talk about the computational techniques to modeling and simulation the process variations in integrated circuits and MEMS. This thesis is supervised by Professor Luca Daniel. And this is the outline of the talk. Today I will first introduce why uncertainty quantification is important for integrated circuits and MEMS design. And then in the body part, I will first introduce a stochastic testing method to calculate the uncertainties in integrated circuits and MEMS. And then in the second part of the body section, I will introduce a tensor-based algorithm to calculate the uncertainties for systems with many random parameters. Okay. And then I will conclude this talk by a summary of this talk and also the performance of the simulator. We all know that due to the advancement of the fabrication process, the transistors on a single chip have been increased from several thousand to several billions. The driving force is obviously the advancement of the fabrication process. But another driving force that we cannot see obviously is the revolution of the design methodology. If you look at the design style in the early stage, in 1960s and 1970s, most of the chip designs were finished manually. In that case, people can only design circuits with a small number of transistors. And then, both in academia and in industry, some pioneers asked one question: can we design integrated circuits using computers? In 1960s and 1970s, this idea was thought as crazy, and most people in industry doesn't believe it was possible. Okay, and then there was a milestone in 1973 at UC Berkeley. Dr. Nagel released the first version of SPICE, and then it became widely accepted by both academia and the industry. Since then, many efforts have been made to investigate algorithms such that we can use computers to help design chips. Nowadays, due to the electronic design automation software, we can integrate billions of chips, billions of transistors on a single chip. And if you look at the modern electronic design automation software, there are many functionalities. We have layout software. We have optimizer for circuit design. We have the physical design tools. All of these functionalities rely on fast modeling and the simulation engine. So actually, numerical modeling and the simulation plays as a backbone of the EDA software. Nowadays, we have a big challenge in the electronic modeling and the simulation. We have the process variation. Because we are doing design in the nanometer scale, so even a random difference at the nanometer scale can have a large impact on the electrical property. For instance, we have the surface roughness, we have the imperfect lithography, and in the transistor fabrication, we have the geometric variability and also have the random doping effect. All of these variabilities can propagate to the chip and the circuit level. So if we look at the yield diagram of the wafer, we may find that many chips may not work properly. And if we look at the chips fabricated by the semiconductor industry, we may find that many chips do not satisfy the signal delay or power specifications. So this is a big challenge. To solve this problem, we need to use rigorous uncertainty quantification approach. Assume that we have the process variations. Assume that we know, for instance, the distribution of the process variations. This can be done, for instance, by some experts working on the process modeling, for instance, Professor Duane Bonnet's group. And then assume we have a computational model. This computational model here is just a general abstraction. You don't need to care about the mathematics. It's just, for instance, a circuit equation describing the network, or Maxwell equation describing the microwave devices. And we want to simulate this computational model so that we can predict the statistic behavior of the chip before the fabrication. Okay, this is a forward problem. We have the process variations, and we want to predict the statistic performance of the whole chip. Sometimes we are also interested in the inverse problems. We have the measurement data of many chips, and we want to model a new generation process variations. And in the mainstream electronic design automation algorithms, electronic design automation softwares, most of the stochastic simulation algorithms are implemented by Monte Carlo. In Monte Carlo, people first generate some random samples according to the process variations. And then they call a SPICE or any other software, for instance, Consolve, to simulate a chip by many times. And then they get a bunch of solution samples. After they getting the solution samples, they analyze the samples to extract some statistical information, for instance, the density function or the moments. The nice property of Monte Carlo is that it is very easy to implement because we don't need to care about this part. We just need to care about how to draw the samples. But the main limitation is that we may need too many samples, and thus we need a long time simulation. But if we look at the problem outside of the box, we find that sample is only one way, but not the unique way to represent the uncertainties. We have many other choices. For instance, we can use moments if we want to make a decision about the price of the chips. And we can use density functions if we want to estimate the yield or optimize the yield. In this talk, I will focus on the surrogate model, which is a model that is very efficient to evaluate. And I will explain why. If we look at a higher-level picture, we have a computational model. But this computational model may be used for some other engineering tasks. And this computational model can be called many times to generate a large number of samples. For instance, sometimes we want to analyze the yield of the chip. In this case, we need to call the simulator many times to get a large number of samples to characterize the statistical behavior. Sometimes we want to optimize the design. In this case, we want to call the simulator many times to tune the design parameters. In the inverse problem, we want to infer the process variations. And then we also need to call this computational model iteratively, such that we can get a good sense about the process variation. On the other hand, if we look at the computational model itself, consider that we want to get a single sample. It can also be very expensive because the computational model may be a large-scale differential equation. For instance, a partial differential equation or integral equation describing the device physics. If we have a large network, we may also have a dynamic system describing the whole network. So in summary, even if we want to do one single simulation, it can be very expensive. So the key idea is that instead of using the original computational model, we replace the original computational model by a surrogate model. If the surrogate model is easy to evaluate, and then we can accelerate the whole engineering design task. Now I'd like to present the first method to generate such kind of surrogate model. And it's specified for the nonlinear circuit with process variations. And I'd like to begin by specifying the computational model, because at the beginning, I give the computational as an abstraction. And now I will show the specific form of the computational model for circuit problems. We focus on the dynamic networks. Dynamic networks can be used to describe many engineering problems. For instance, the US gas pipeline is a large network. The neural system is a large network. The electronic circuit is again a network. Although the physics behind these networks can be entirely different, but they all can be modeled by a differential algebra equation. Don't care about this equation. Okay? In this equation, you only need to care about two things. The first thing is a random parameter C that describes the process variation. The second one is the unknown variable x. It describes the voltage or current of the circuit. And now I'd like to use a simple example to explain this computational model. We consider a simple RC example. In this RC example, we assume that the resistor is influenced by some process variations. So the resistor itself is a random parameter. Okay? We don't know the value of the resistor. It's just a random parameter. And we want to compute the voltage at node 1. To compute the node voltage, we first need to know the currents. Okay? The first current flows from the resistor. It is a static term in the computational model. The second current is due to the charge and discharge of the capacitor. is a dynamic term of the computational model. So this computational model is very complicated, but on the other hand, it's very simple because it's just Kirchhoff current law and Kirchhoff voltage law with some device equations. Now we want to generate a surrogate model, and we describe the surrogate model by the generalized polynomial expansion. And here, the left-hand side is the voltage or current we want to compute. And they are dependent on the process variation Kc. We want to approximate the voltage and current by some orthonormal polynomials as the basis functions. Here, psi is the basis functions. They are orthonormal to each other. Because they are orthonormal, so similar to vector, we can get the coefficient by a projection. This looks a little bit complicated, right? But we can compare it with Fourier series expansion. In signal processing, we know that if we have a periodic signal, then we can approximate the signal by increasing the order of Fourier series expansion. If we increase the number of the basis functions in the Fourier series expansion, we can get more and more accurate approximation of the waveform. In the generalized polynomial expansion, we can also increase the number of the basis functions. As we increase the number of the basis functions, then we can approximate the density function of the unknown variables with a higher and higher accuracy. So what's the difference? In Fourier series expansion, we want to approximate the signal. In the generalized polynomial expansion, we want to approximate the stochastic behavior. Now we have the form of the surrogate model. We have specified the basis functions. What we want to compute is the coefficient for each basis function. There are two main classes of solvers to solve this problem. The first kind of solver is sampling-based technique, such as stochastic location. And the second kind is long sampling-based technique. They are called stochastic allocation. Both kinds of techniques have been applied to solve linear and nonlinear problems with process variations. In this talk, I will introduce a new technique called stochastic testing, and I will show its application in nonlinear circuits. Because the nonlinear circuits is the generalization of linear circuit. So if it applies for nonlinear circuits, it's also OK for linear circuits. Before jumping to the details, I like to give the main idea. So forget about the mathematics, just focus on the main idea. We have the original circuit equation. In the original circuit equation, we want to compute the voltage and current dependent on the process variation Kc. This is the original problem. It's a stochastic problem. What we want to do is that we apply stochastic testing to build a new differential equation. In the new differential equation, we don't have any random parameters. We don't have any uncertainties. So the new equation is a deterministic equation. And in the new equation, the unknown variables are x hat, x tilde. X tilde contains all of the coefficients in the surrogate models. So the basic idea is that instead of directly computing the voltage or current, we compute the coefficients inside the surrogate model for voltage and current. And I'd like to first show one simple example for this simulator. This is a no-noise amplifier with 3 random parameters, and they are long Gaussian. And this diagram shows the convergence of this algorithm. You don't need to care about that. Just focus on this part. Using this simulator, if you want to characterize, for example, the DC behavior of this circuit, our simulator can finish the simulation in 0.4 seconds. OK. What about Monte Carlo? If you look at Monte Carlo, to do the same simulation to achieve the similar level of accuracy, Monte Carlo needs 40 minutes. OK. So now I'd like to explain how to get this kind of performance. Again, I begin with a general stochastic model. You can just regard it as a circuit equation. In a non-sampling based simulator, the key idea is to generate a deterministic equation instead of the original stochastic equation. Okay. In the deterministic equation, we want to compute the coefficient inside the surrogate model. Because we have m groups of unknown variables, so in the equation, we should also have m groups of equations. So the key problem is how to construct each group inside this equation. The key idea is that first we apply the generalized polynomial expansion to the original computational model. And then we have a function. Then we choose a test function, which is also a function of the random parameter. We need to enforce the first function orthogonal to the test function. So we have a constraint. Now for each block, we have one constraint. For m blocks, we have m constraints. Now the problem is solvable. We have m groups of unknown variables. We have m constraints. So the problem is solvable. Now I'd like to introduce a little bit of details. The first key problem is how to choose the testing functions. In the simulator, the test functions are chosen as some delta functions. It is the impulse at one point and 0 anywhere else. By using these testing functions, a nice property is that the simulator has a linear computational complexity with respect to the number of basis functions. And the second problem is how to choose this sample to define the testing function. I use two steps. The first step is to generate some multidimensional integration points, and then a subsample some dominant samples to make sure that we have the same number of samples as the number of basis functions. Because we have m groups of unknown variables. We also need m groups of equations. So we need m testing functions. This is a more detailed result for the transient simulation for the low noise amplifier. Using this simulator, we can calculate the mean value, variance, or even the probability density function for the waveform at each time point. And to do this simulation, our simulator requires less than 1 minute. And if you use Monte Carlo, if we want to characterize the full statistic for each time point, Monte Carlo needs several days. And based on this simulator, I further developed the solver for simulating the power electronics and communication circuits. In power electronics and radio frequency circuits, if we look at the waveform, we are mainly interested in the steady state. And an interesting phenomena of power electronics and radio frequency circuit is that in most cases, the steady state is a periodic signal. So the signal repeats after a certain cycle. If we use transient simulation to simulate this behavior, the transient behavior may experience a long time. So this means that if we use transient simulation, we need to do a long time of computer simulation. So the trick is to ignore the transient behavior and directly compute the steady state. There are some existing algorithms to solve the deterministic problems without process variations. Interestingly, this phenomena widely exists in nature and science. For instance, in cardiovascular systems and in neural systems, there are also many periodic steady-state behaviors. Okay, now I'd like to consider the more complicated problem. We consider the oscillator. Oscillator is special because the input signal is constant. The input signal does not have a period. And we want to consider an oscillator with uncertainty. So now, if we look at the waveform, there are two properties. The first property is that the waveform will oscillate. The input signal does not have frequency, but the circuit will oscillate by itself. The second property is that with uncertainty, if we look at the waveform, for different value of the process variations, the oscillator has different frequency. So if we look at all of the waveforms, they don't have a unified frequency. Okay. Now to compute the frequency, we first rescale the waveform by defining a scaling factor such that the waveform has a fixed period on the new time axis. And we define the new waveform as z, and we define the scaling factor by AXZ. Now we compute two unknown variables. The variable is the waveform on the scaled time axis z. The second term is the scaling factor a. The first term can characterize the variation of the waveform, for example, the magnitude of the current or the voltage. And the second term can capture the variation of the period and the frequency. And this is one example, a copious oscillator, and it has two random parameters. By this stochastic circuit simulator, we can obtain the distribution of the frequency in less than 10 minutes, in less than 10 seconds on MATLAB. Okay. But if we use Monte Carlo, it requires about 1 hour to do this simulation. Okay, I have finished introducing the first simulator, and now I will focus on the more complex problems with design hierarchy and with more random parameters. If we look at many practical engineering problems, many problems are designed in a hierarchical way. For instance, if we look at this chip, inside these chips, there are many devices. For instance, inductors, MEMS devices, photonic devices. So if we want to characterize the statistics of this whole chip, we first need to characterize the uncertainty of each device. So we need to construct a stochastic model for each device. And then we do a circuit simulation to characterize the uncertainty of the whole circuit. The second step can be done by our stochastic testing simulator because the chip is a network. And the main challenge is how to solve the problem in the first step. Again, I'd like to begin by specifying the computational model for device modeling. There are many kinds of devices in the chips. Physically, they can be entirely different, but mathematically, they can be described by partial differential equation or integral equation in the similar form. And then, using some numerical technique, we can convert the mathematical description to a linear equation dependent on some random parameters. The main challenge is that in the linear equation, we have a huge number of random parameters. So we need high-dimensional stochastic solver. Here, high-dimensional means a lot of random parameters. To solve this problem, there are three main classes of solver. The first class explores the sparsity of the surrogate model. If we consider high-dimensional case, the coefficients of many basis functions are close to 0. That is sparsity. The second class of solver using reduced order model technique to accelerate the computation. And the third class exploits the low-rank property of the governing equation. And now I'd like to introduce a new technique which exploits the low-rank property of the simulation sample. Okay, I'm not exploring the low-rank property of the governing equation. I'm exploring the low-rank property of the simulation samples. We consider the stochastic collocation technique. Just forget about this part. We focus on this part. Okay, we focus on this part. To compute the coefficient for surrogate model, we need a numerical integration. And in the numerical integration, we need a huge number of integration samples, QCL. And for each integration sample, we need to do a device simulation to get the output of device Y. So the key problem is that we need to develop a fast method such that we can use a small number of samples. If you look at the integration rules, the standard technique can only handle problems with 10 random parameters. Using sparse grid, we can handle maybe 20 to 30 random parameters. For high-dimensional case, Monte Carlo seems to be the only choice, but it has a low accuracy. So Monte Carlo is used if we don't have any other choice. If we have a better choice, we'd like to use a more accurate algorithm. This is a motivating example. We consider the MEMS device with 46 process variations. And to compute the coefficient in the surrogate model, we need to compute a 46-dimensional integration. This is a very high-dimensional integration. And assume that for each parameter, we use 3 samples to compute the numerical integration. And let's look at how many samples we need for these examples. If we use sparse grid, we need 75,000 samples to do the simulation. If we use the standard integration technique, we need this huge number of integration samples. We cannot even store all of the data on the computer. And we develop an algorithm, tensor recovery. We can do the simulation using only 300 samples with only 0.1% error. Now I'd like to explain how to do this. The algorithm is based on the concept of tensor. We know that if we have a matrix is a representation of 2-dimensional data arrays. It has row index, column index, and for each index, we have one data. That is a matrix. We can generate this concept to 3-dimensional case. We can define a 3-dimensional data. For each element, we have 3 index. One index in x direction, and another in y direction. We also have z direction. Example is multiple slices of the MRI image. One slice is a matrix. Multiple slices are a tensor. We can further generalize this idea to a high-dimensional case. Assume that we have d index, so we have a d-dimensional tensor. We look at the samples in the numerical integration. Each sample is one index in a d-dimensional tensor. So actually, we can represent all of the solutions for the integration samples by a single tensor. But the problem is that we cannot compute the tensor, because for each element, we need to do one simulation. This tensor just has too many elements. We cannot do all of the simulations. And this table shows how many samples we need to simulate to get the full tensor. We can see that if we increase the number of random parameters, we need this number of simulation. It is impossible. Instead of directly simulating all of the samples, I use the tensor recovery idea. The basic idea is that this considers a 2-dimensional case. Instead of simulating all of the samples, we simulate only a small number of the samples. Okay, in this matrix, we know some value of the elements. They are the simulation result of the devices. But we don't know the value at other places. So a key idea is that we want to use the available simulation data to predict the simulation result for all of the other samples. This problem can be formulated as an optimization problem. We want to compute the tensor to approximate the unknown tensor. But the problem is ill-posed because let's consider the unsimulated solution samples. Actually, we can assign any value. We can assign any value to this position. So we need to regularize this problem by adding some constraint to the unsimulated samples. We first employ the low rank property. We know that if we have a low rank matrix, it can be represented as a sum of some rank 1 matrix. And each rank 1 matrix can be represented by the outer product of 2 vectors. Okay, this is the low rank property of matrix. And we can generalize it to the case of tensor. This is a low rank decomposition for a 3-dimensional tensor. And this is a rank 1 tensor. We can further generalize to the high-dimensional case. So we apply the first constraint. The first constraint is that the simulation data has a low rank property. So they can be represented by a set of vectors. And the second constraint is that if we look at the surrogate model, we look at coefficient in the generalized polynomial case expansion. In the high-dimensional case, we find that most of the coefficients are close to 0. So we also have a sparsity constraint. Now we have 2 constraints. The first constraint is the low rank property of the simulation data. The second constraint is the sparsity of the surrogate model. Now we combine the 2 constraints together. We get a regularized optimization problem. And in the optimization problem, we only need to compute some vectors instead of the whole tensor. Because we need to only need to compute the tensors, we only need to compute the vectors, the number of unknown variable is a linear function of d. D is a number of random parameters. It's not an exponential function of the number of random parameters. Now let's compare it with the standard integration method. In the standard integration method, the unknown variables grow this way. It's crazy. If we look at the low rank optimization problem, the complexity grows linearly. We can see that if we compare these in this column, we compare these 2 data sets, the complexity reduction is significant. Now I'd like to show the detail of these MEMS devices. And again, it has 46 random parameters. And these 2 figures show the convergence of the optimization algorithm. And this figure shows the surrogate model. We can see that it has a very sparse property. And this figure shows the computed stochastic behavior. And if we compare it with Monte Carlo, we cannot tell the difference. But to use Monte Carlo to get this statistic behavior, Monte Carlo will be 60 times slower, 16 times slower. We further incorporate this device, this MEMS device, in a MEMS IC co-design problem. And this MEMS switch acts as a MEMS capacitor. And we use this MEMS capacitor to build an oscillator. Because each MEMS device has 46 random parameters. Now, let's look at the whole circuit. The whole circuit has 184 random parameters. So if we use a third-order surrogate model, and then we need 1 million basis functions. We cannot construct such complex surrogate models. But using the stochastic model and use a hierarchical approach, we can capture the statistics of the whole circuit very easily. On MATLAB, we can simulate this circuit, this oscillator circuit, in 10 minutes. And if we use Monte Carlo to achieve the similar level of accuracy, we need 15 to 16 hours. Now I'd like to summarize this talk. I first explained that process variation is a big challenge in the nanoscale chip design. So we need to calculate the uncertainty before the fabrication. And I further explained that the surrogate model is very useful for many of the engineering design problems. And then in the first part of the body section, I introduced a stochastic testing simulator for nonlinear circuits with process variations. It can be used for DC, AC, transient, and periodic steady-state simulation. And in the second part, I developed a tensor-based technique to solve design problems with many random parameters. And I have shown its application in MEMS devices and in MEMS IC co-design. And I'd like to summarize the performance of the simulators. Firstly, for the problems with a small number of random parameters, we can directly apply stochastic testing to easily obtain a speed of a factor up to 1,000 times. For high-dimensional problems, for high-dimensional and complex problems, it's very challenging, but using some tensor technique and some other possible techniques, we can still gain a speed of a factor of about 100 times. Lastly, I'd like to acknowledge the support from my supervisor, Luke Daniel, and my CIS committee member, Professor White, Professor Dwayne Bonin, and Professor Kanidakis from Brown University. And the research is in collaboration with many guys inside and outside of MIT. Thanks. I'd like to answer any of your questions.
Very exciting talk, and it's open the floor for questions. Go ahead.
Thank you for a very interesting talk. Does this technique have any specific type of circuitry that it applies to? For instance, does it apply to chips that are entirely digital with chip counts of 1 million, or is it more applicable to maybe a smaller chip count that has a hybrid circuit between analog and digital? That kind of, what realm does it apply to most?
In this talk, I mainly show the application in analog circuits and RF circuits. We have tested the simulator by some digital cell circuits. For example, the SRAM cells. But we have not yet tested the large-scale circuits. For large-scale circuits, maybe there are some new challenges. We are not sure, but it works for the digital cell design.
Hey, so in the third part of your talk, you mentioned trying to attack very high-dimensional problems by exploiting low-rank tensors, right? And
right.
So essentially, you have an optimization problem where
right.
you regularize it by using low-rank and you regularize it by using sparsity.
Right.
But the title of that section, you had the word hierarchical.
Right.
I was just wondering which part of that did you build in the hierarchy of the circuit, right? So in a real problem where you have multiple layers, how would that be exploited to potentially solve the optimization problem?
The key is that, okay, first we use low-rank tensor technique to model each device. And then we use a high-dimensional device model inside a higher-level simulator to simulate a big system. That is a hierarchical simulation. In this talk, I didn't show the details of how to do that. And incorporating the device model, we cannot directly incorporate the device models in the circuit simulator because we need to change the basis functions. We need to change the variables. In that part, we also have high-dimensional problems. But due to the time limitation of this talk, I only show the flow. I only show that it can be used in the hierarchical design, for example, in the MEMS IC co-design. But I didn't talk about the mathematical details of how to do it.
So you actually applied it to the hierarchy?
Right, I apply to a hierarchical problem, the mem-size co-design problem.
Any other questions from the audience? Well, I have a quick question for you. By all means, this is not my topic of expertise, but I'm interested on the future. So maybe if you can elaborate in a few words, what's the future for this work regarding implementation into real products and tackling the harder problems that you were mentioning at the very end?
Okay, I'd like to advertise my work. I'd like to say that this is there are lots of opportunities in this direction. Okay, firstly, as pointed out by this guy, we don't know how it behaves for large-scale digital circuits. This is one challenge. The second challenge is inverse problem. Model the process variation. That is, we have this simulator, but we are not doing SPICE. We are doing the inverse of SPICE. In SPICE, we have the variability, and we want to characterize the behavior of the circuit. But if we want to inverse SPICE, we have the behavior of the circuit. We want to find out what happened at the device level. This is a very challenging problem. And there are also other problems. For example, how to use this stochastic simulator to optimize this circuit. And even if we want to expand the topic, we can extend this simulator to simulate power systems, to simulate neural systems, and many other problems.
Well, thank you so much. We ran out of time, but let's thank Zhang again for his excellent PhD work. With this, we finish this term seminar. Thank you so much for your attendance, and I'll see you in the spring.